everyone. Welcome to Robert Morris University Math 0900, Chapter 4, Lesson 2. This is Brianne Pernick. We are now going to work on our lesson on negative exponents and scientific notation. In this lesson, I do need you to make sure that you understand the terms negative exponents, scientific notation, and significant digits. In the last lesson, we did talk briefly about using negative exponents. The book wanted you to use part 2 of the division rule, where when the exponent in your denominator was larger than the exponent in your numerator with like bases, they wanted you to subtract the denominator first and then just simply keep that value in the denominator. I proposed to you that you could subtract in the same order that we were used to. And then when you had a negative value, recognize that that was not simplified and plop that value into the denominator, make the exponent positive, and put it underneath a 1. This is part of the definition of a negative exponent, only I didn't tell you that in the last section. Negative exponents are considered to be unsimplified and cannot be used in an answer. You must learn how to simplify them using the laws of exponents that were covered in section 4.1 and the properties of negative exponents that we're going to go over shortly. Okay, so what we're going to talk about here is, and you should recognize from what we talked about in section 4.1, is that when you have a negative exponent, it's considered to be an unsimplified expression. And when you have a negative exponent, basically what's going to occur is it's going to switch from its location. If it's in a numerator, it is going to switch its location and go to a denominator, and the exponent will then become a positive exponent. So right now we have y to the negative 3. We're going to put that underneath a 1 and write that as y to the 3rd. In letter B, we have z to the negative 6. That is an unsimplified expression. So we will put it in a denominator underneath a numerator of 1, and in order to make it into a positive exponent, we would write it as z to the 6th. Letter C, we have w to the negative 1. Again, we would make the numerator 1, and we would have w to the 1st power. So whenever, excuse me, whenever that exponent is negative, it has to switch its location from that numerator to the denominator. You're going to write the exponent as positive, and then your numerator would simply become a 1. Now, variables aren't the only ones that follow this rule. Numbers that are written with negative exponents must be taken one step further in order to be simplified as well. So what I'd like you to do is go ahead and follow the pattern that we've just been following, and then evaluate that exponent as well. Go ahead and pause the recording and see what you come up with, and then we'll come back together and check your work. Okay, by now you should have had an opportunity to evaluate letters A and B, and the first thing that you should have done is recognize that 3 to the negative 2nd power is not simplified. So you would have wanted to rewrite that as 1 over 3 squared. And then to evaluate that, you would simply evaluate 3 to the 2nd power, so we'd have 1 over 9. For letter B, we would want to rewrite this as 1 over 2 to the 5th power, and then we would evaluate 2 to the 5th power as 1 over 32. Now, sometimes you will encounter negative exponents in your denominator. They are unsimplified as well. So if you have a negative exponent in your denominator, guess what? It's going to switch to your numerator. So when you have a negative exponent in the numerator, it goes to the denominator. A negative exponent in the denominator goes to the numerator, and then it becomes positive once it makes that switch. So what that property states is that after you've simplified your exponents through multiplication and or division using the product rule, the quotient rule, raising a power to a power, raising a product to a power, raising a quotient to a power. All of those exponent laws that we covered in section 4.1. If you have any negative exponent left, and if it's in a numerator, it must switch to the denominator in order to become positive. If the exponent is left in the denominator, it must switch to the numerator in order to become positive. Remember that you can never leave a negative exponent in your answer because they're considered unsimplified. So we're going to look at a bunch of examples right now. And what we're going to do is write the expression with absolutely no negative exponents. We're going to start with example A. We have 1 over x to the negative 6. We do not want to have any negative exponents. I always say that negative exponents are unhappy. They want to switch positions so that they can become happy. So the negative exponent is in the denominator. It wants to go up to the numerator. So it's going to switch to the top. If you want to think of that as your fraction, right now it's down here. It's going to bump up top and make itself be an x to the 6th. Now, since we already had a numerator of 1, when you do 1 times x to the 6th, you're still just going to have x to the 6th. So that's your final answer. Now, letter B. Every single one of those individual factors have a negative exponent. That means every single one of them is going to switch positions. So our x cubed, or our x to the negative 3, is going to go to the denominator and become x cubed. Y to the negative 2 will go to the denominator and become y squared. Z to the negative 4 will go to the numerator and become z to the 4th. Now that everything has switched locations and become a positive exponent, it is now considered simplified. Why don't you go ahead and try letter C? Remember that only the terms, or the factors I should say, that have a negative exponent need to switch positions. Go ahead and pause the recording, try letter C, and then we'll check your work. Okay, by now you should have had an opportunity to complete letter C, and you would notice that only the x to the negative 2 has to switch its location. So that means that y cubed is going to stay where it is in the numerator, and x squared is going to jump down to the denominator and become positive. Okay, letter D is just a slightly different example, and the reason being is that we have to apply the power to a power rule because we are raising that entire quantity to the power of negative 3. So we're going to have 3 to the negative 3rd. We're going to have x to the 12th, because remember, the product rule states that we multiply. So we're going to have negative 4 to the negative 3, and we multiply those. And then we have y to the negative 6 power, because we do 2 times negative 3. And now we're going to, now that we have taken care of raising our powers to a power, we're going to move things around. So I'm going to draw my fraction bar, and anything that has a negative exponent is going to switch its location from the numerator to a denominator. So 3 to the negative 3 needs to switch. So it's going to become 3 to the third. X to the 12th already has a positive exponent, so it can stay right where it is. And y to the negative 6 needs to jump down to the bottom, and its exponent becomes positive. Lastly, I just want to evaluate 3 to the third power. So we have x to the 12th over 27, y to the 6th, and that is my final answer. Letter E. Before we start this problem, we want to start by using the quotient rule. So we're going to keep our bases the same and subtract our exponents. So we're going to start by doing x to the 2 minus negative 5, and then we have y to the negative 4 minus 3. That becomes x to the 7th, y to the negative 7th. Does anything need to switch positions? Sure does. X to the 7th stays where it belongs. Y to the 7th needs to jump down to the denominator so that that exponent can become positive. You need to make sure that you understand how to simplify negative exponents. If you are unsure of how I did these examples, please contact me so that we can do some more work together. The next topic that we are going to cover is scientific notation. Scientific notation is a mathematical notation that is used to express very large as well as very small numbers, and it's very common and it's a very common use, I should say, of negative exponents. Excuse me. So, scientific notation takes a positive number, and it's written in scientific notation if it is in the form of a times 10 to a power, where a has to be larger than 1, but smaller than 10. Okay, greater than or equal to 1, but smaller than 10. So in other words, the number that we use whenever we convert a number to scientific notation can be 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's it, okay? Anywhere in between there. So 1 all the way up through 9.9999999. We can never go larger than that. It has to be smaller than 9. So as we're looking at this, and we have 4,567, right now our current decimal point is right here at the end of our number. To convert into scientific notation, we have to pick that decimal point up, and we're going to move it so that we create a number that is just has a ones place. So the first thing that we have is 4.567. Remember that it has to be a 1 point something, 2 point something, 3 point something, all the way up to a 9 point something. It can never be bigger than a 9 point something. And then we're going to write times 10 to some power. Well, how do we figure out the power? You figure out the power by counting the number of decimal places that you moved. We moved 1, 2, 3 decimal places, so it's going to be 10 to the third power. For letter B, Our decimal point was here at the end. We have to move it so that we will create a new number that is going to either be a 1 point, 2 point, 3 point, 4 point, all the way up to 9 point something. Okay, so we're going to pick this decimal up and move it so that its new location is right there after the 1. So I'm going to have 1.57. You write every digit after that 1 until the last non-zero digit. So we have 1.57 times 10 to the what power? We need to count those places. So we have 1, 2, 3, 4, 5, 6, 7, 8. We jumped 8 places, so it's 10 to the 8th power. Why don't you go ahead and try letter C for me? Pause the recording, convert letter C to scientific notation. Okay, by now everyone should have had an opportunity to convert letter C to scientific notation. So what you should have done here is taken your decimal point and moved it all the way back here so that it was between the 8 and the 2. So we should have 8.276 times 10 to the 1, 2, 3, 4, 5, 6, 7th power. Excuse me. Now please notice that every example that we did in A, B, and C were large numbers. These were numbers that were greater than 1. We were dealing with pretty big numbers. Whenever you were moving your decimal point to the left, okay, you are always going to have a positive exponent because you're dealing with very large numbers. Okay? However, whenever you are dealing with decimals, numbers that are smaller than 1, you are going to deal with negative exponents. We are now going to be dealing with very, very small numbers. We're going to follow exactly the same pattern of what we just did. We want to pick up our decimal and we still want to move it so that we're creating a number such as a 1 point something, 2 point something, 3 point something. In this case, it is a 6.1. We're still going to have times 10 to some power. How many places did we move it? 2, but this time it's negative 2 because we moved our decimal point to the right. Letter E. We're going to pick that decimal point up and move it so that it's in between the 5 and the 2. So we're going to write 5.2 times 10 to the 1, 2, 3, 4, 5, 6 to the negative 6th power. Please try letter F for me. Pause the recording, complete letter F, and as soon as you're ready, hit play. Okay, by now everyone should have had an opportunity to complete letter F. You should have picked that decimal point up and moved it all the way over here in between the 1 and the first 7. So we should have 1.778 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10th power. Excuse me, negative 10th power. Remember, anytime that you are moving your decimal point to the right, that is going to be a negative exponent, and we're dealing with those decimal values. If you're moving your decimal point to the left, it is going to be a positive exponent. Now that you know how to write in scientific notation, it is also extremely important for you to be able to go the other direction and write in decimal notation. So letter A shows us that when we're given scientific notation, we should be able to write it in decimal. So if we have 1.568 times 10 to the second power, this tells us how many places to move that decimal. So we're going to pick it up and move it 2 places. So we're going to have 156.8. Remember, if your power is positive, your number should be getting bigger. Okay, your number should be getting bigger. You're going to move that decimal point to the right. Now, for letter B, we have a negative exponent. That means we have to pick that decimal point up and move it to the left because we need to create a decimal. So we're going to go 1, 2, 3 places and draw it in. So we're going to, and those loops that we made will fill in with zeros. So we're going to have 0.0074332. Please pause the recording and complete letters C and D. Okay, by now you should have had an opportunity to complete letters C and D, and you should be ready to check your work with me. For letter C, you should have recognized that that is a negative exponent, so you wanted to pick that decimal up and move it 8 places. So we have 2, 3, 4, 5, 6, 7, 8. So we need to fill those loops in with zeros. So I need to have 1, 2, 3, 4, 5, 6, 7 zeros, and then my 9, 3, 1. And then for letter D, we have a positive exponent, so we are moving in the opposite direction so that we can create a larger number. So we should have 530,400. And then just a real world example for us here. We have that a light year is a distance of this very large number here, meters. Write this in scientific notation. Excuse me. So what you would want to do with this is put your decimal in, and we're going to want to move it all the way right there. Go ahead and take a minute, convert that number into scientific notation. By now you should have converted the light year distance into scientific notation, and you should have had 9.46 times 10 to the 15th power. Okay. Now, numbers that are written in scientific notation can be multiplied and divided together while they are written in scientific notation form. To do this, we will use the laws of exponents, and this is where scientific notation becomes extremely useful. If you think about having those numbers that are very, very large or very, very small, it would be an extreme pain to have to deal with all of those zeros, as in the light year, or think about that decimal that we had that had all of those zeros in it. I think there were like 10 zeros. It would be really hard to keep that organized and to manipulate that within a problem or plug it into a calculator. Imagine how hard that would be. If we convert our work into scientific notation and use our laws of exponents to help us, it makes our work really easy. And the way that we do this is by first multiplying those two numbers, and then lastly using the laws of exponents to multiply the last numbers. So 3.2 times 1.5. We need to go ahead and take care of that math. So please do that math for me. Okay, you should have gotten 4.8. And then after that, you're going to use your laws of exponents to multiply 10 to the 7th times 10 to the 12th. When your base is the same, you're going to keep the base and add your exponents. So 7 plus 12 makes 19. You check to make sure that your 4.8 is in proper scientific notation, and it is a 4 point something, so it is an acceptable form of scientific notation. So we're good to go there. And then lastly, in B, we follow the same procedure. We're going to divide those numbers, and then we use our laws of exponents to divide the bases. So 6.3 divided by 2.1 is 3 times. We keep the base the same and subtract the exponents. So -4 minus -2 makes 10 to the -2nd power. And then that is how we're going to multiply or divide numbers that are in scientific notation. It does make it much easier than trying to put them in standard form and work with numbers that are very, very large or very, very small. Now, one last topic here. Whenever we are using scientific notation, we often have to approximate numbers. And we must include some zeros so that the decimal point can be properly located. However, all other digits except for these zeros are considered what's called significant digits. If you look at the number 34.56, which is right in the middle of this paragraph that I'm reading from right now, this number has 4 significant digits. However, the number 0.0049 only has 2 significant digits. All of those zeros in that number are simply considered to be placeholders. The number 634,000 has 3 significant digits, unless we have specific knowledge to the contrary. Those zeros are also considered to be placeholders. Sometimes we round numbers to a specific number of significant digits. For example, if we have 0.08746 rounded to 2 significant digits, we would make that 0.087. If we rounded 1,348,593 to 3 significant digits, we would get 1,350,000. So let's look at an example here. The approximate distance from Earth to the star Polaris is 208 parsecs. A parsec is a distance of approximately 3.09 times 10 to the 13 kilometers. How long would it take a space probe traveling at 40,000 kilometers per hour to reach the star? And they want us to round it to 3 significant digits. So the first thing that we would want to do here is convert our parsecs into kilometers to make this problem useful to us. Being that our space probe is traveling in kilometers per hour, we need to figure out the distance from Earth to Polaris in kilometers. So we're going to start by taking 208 parsecs, and we're going to multiply that by 3.09 times 10 to the 13 kilometers, because that's the conversion to get from parsecs to kilometers. Okay, 1 parsec is 3.09 times 10 to the 13 kilometers. That's what they told us. So when we do that math, remember, you're going to multiply your whole number by your whole number there. Okay, you should get 624.72 times 10 to the 13 kilometer. That number represents now the distance from Earth to Polaris in kilometers. Okay, we can write that up here to help us remember what that number is. That's Earth to Polaris. Okay, now if the next thing that we would want to do here is focus on the distance formula, D equals RT. And the reason I suggest this is because we know the distance from Earth to Polaris, and we know the speed that the space probe is traveling, and what we're looking for is the time that it's going to take that probe to get there. So I'm going to go ahead and pencil in 624.72 times 10 to the 13 for my distance. And my rate is 40,000 kilometers per hour times my time. In order to solve for time, we want to divide by 40,000. Actually, before I do that, why don't we convert that into, let's make this a little bit easier on us. Let's convert that into scientific notation in this step. If I put this into scientific notation and I make it 4 point something, that would be 4 times 10 to the what? 1, 2, 3, 4. 10 to the 4th. So those are going to cancel, and I have 4 times 10 to the 4th. Okay, so now let's divide 624.72 times 10 to the 13 by 4, and then we're going to use our quotient rule. I would like to pause the recording and have you guys finish off this problem to figure out how much time it's going to take. Okay, as you were working through this and you did your division, you should have had 156.18 times 10 to the 9th power. However, this is not in scientific notation, and the reason being is that we can't leave it as 156 point. We need to pick up this decimal point right here and move it backwards 2 places. So this is going to become 1.5618 times 10 to the, now since we moved it back 2 places to the left, that's going to bump up our power 2 places, 10 to the 11th. So that's our answer so far. But it said round to 3 significant digits. So we have 1.56. There's our first 3 significant digits, and we want to round right there. So we have 1.56 times 10 to the 11th hours. Oh, that should be an R. equals our time. So that concludes our lesson on scientific notation and negative exponents. If you have any questions on any of the concepts that we covered in this lesson, please feel free to contact me. Thank you.